series. Today, Joe Meagher will tell us about Bayesian ancestral reconstructions with applications to bad echolocation. So, Joe is at UCD Dublin, and he was a PhD student here at Warwick just not so long ago, right?
Yeah.
So go on, Joe.
Okay, thanks very much for the introduction, Yuri. Yeah, so I am currently a postdoc at the Insight Centre at UCD, started there in May. But the work I'm talking about today is my doctoral research, which I finished up this year, graduated in July. So yeah, the work was undertaken at University of Warwick, and it was supervised by Mark Gerlami and Theo DeMullis. And it was a collaboration with Kate Jones, who's in UCL at the Centre for Biodiversity and Environmental Research, and it was funded by the EPSRC. So in the following, I'm going to just give a talk a little bit, introduce bats, because this is the application area that the work was focused on. I'm then going to move into some models for evolution and the approach that we took in that respect. Going to talk a little bit about signal processing and how we consider bad echolocation calls in that context, and then I'll finish up by just demonstrating the results and how we went about reconstructing the bat echolocation call. Okay, so the whole concept of this research is that we have observed the echolocation call recordings for some set of extant bat species. And the question is, given that data, these existing bats were able to observe, what did the most recent common ancestor for those bats sound like? What sort of echolocation call did they have, and how was it structured? And could we possibly fill in those various different structures all the way through the evolutionary history? So just to discuss bats a little bit, there's over 1,200 species of bat and 21 families. So that makes them the second most specialized order of mammals after rodents. They're the only mammals capable of powered flight and are found on all continents except Antarctica. Tend to be crepuscular and nocturnal, so crepuscular is off the dawn or the dusk. And traditionally, they're separated into two suborders, the Megachiroptera and Microchiroptera. So Megachiroptera are the bigger bats. These are the fruit bats, and they tend not to echolocate, although some Megachiroptera do use tongue clicks to echolocate, which is a little bit different to the laryngeal echolocation used by Microchiroptera. So bats have been a topic of scientific study since about the 1790s, when it was established that blinded bats were able to navigate. The fact that they used echolocation, ultrasonic echolocation calls to do this, was established in the 1940s by Donald Griffin. They are of particular interest because they're keystone species in a lot of desert and tropical habitats. They're pollinators and are part of kind of pest. They act as pest control, giving them an outsized sort of impact on the environment around them. Their characteristics are that they're crepuscular and they fly, and that they echolocate. Echolocation then is a particularly interesting characteristic. It is one that Dawkins actually used as an example of good design by evolution, and has actually been of interest as well in terms of biodiversity monitoring, because it offers a way of doing non-invasive monitoring of bat populations. But that's actually work that Professor Jones was quite heavily involved in at UCL. So the ancestry of bats has actually been a somewhat controversial topic in the past. In the 80s, there were studies done that suggested that actually the fruit bats, the Megachiroptera, were more closely related to primates and colubos than they were to the Microchiroptera, which suggested that we had a paraphyletic group of bats, as you can see there in figure B, what that means. And this was actually credible at the time. It was based on studies of a particular group of nerves at the base of within the brain of the bats. But it was since then studies looking at both morphological and molecular traits have rejected that hypothesis. And our current understanding, and there's a fair bit of consensus around this now, is that all bats have a single most recent common ancestor, which existed between 52 and 66 million years ago. There's a single flying echolocating bat. And so the structure of this evolutionary history is fairly well understood at this point based on molecular data studies of the bat's DNA. So this allows me to kind of set our problem statement. So the idea is, given echolocation call recordings taken from extant bat species, and then given a phylogeny which would have been inferred by molecular data describing the evolution relationships, what can we say about the echolocation call for the most recent common ancestor of those bats? So we make a couple of assumptions. We assume that the diverse species emerged as a result of natural selection, kind of Darwinian natural selection. That, yeah, again, the most recent common ancestor of echolocating bats was itself an echolocating bat. And that the phylogeny that we have inferred from these molecular studies does offer a faithful representation of the evolutionary history of bats. So this is not the first time. Sorry, there was a question there. No? Okay. Okay, so this is not the first time that something that the echolocation, the evolution of echolocation has been studied. Previous attempts have been based on a kind of a best guess based on the physiology of bats, making these sorts of assumptions that we're making here. But yeah, based on the physiology of bats, what is the most likely sort of structure for the echolocation call? But these analyses weren't quantitative at all. There have been a quantitative analysis, but they really struggled with the kind of the considering acoustic signals. Acoustic signals pose a lot of problems for kind of standard machinery within evolution, and also just the sheer volume of data involved. The other point I want to make here is that because we assume a structure for the phylogeny, this is not an application of phylogenetics, or this is not phylogenetics. This is an application of phylogenetics. So I'm actually looking at the phylogenetic comparative method. So the idea is that given a phylogeny, how can we compare the traits across sets of related species? So yeah, that kind of introduced my talk. If there is any questions on any of that, I'm happy to take one at this stage. If not, I'll just continue. Okay. Okay. Well, I will continue on. Sorry, 1 second. Okay.
I don't see your screen anymore. I don't know whether there was on purpose or.
Oh, that is it showing up now?
I still don't see it.
No,
I see his screen.
It's there for everyone else.
It's here for me.
Okay. I'm not sure why that would be the case for you. That's my own.
I don't know.
Okay, I'll continue. Okay, so I'm going to talk a little bit about modeling trait evolution. So in order to understand this, we first consider just a real value trait, that takes a continuous value, so some sort of real value, and we consider the evolution of such a trait along a single lineage of the phylogeny, so from one generation to the next. Our assumption when we model these is fairly simple. It's just that the value of the trait in a given generation depends only on the value of the trait in the previous generation. So this is a Markov property. And then if we then assume that the change from one generation to the next is independent and identically distributed, by the central limit theorem, we actually get a kind of a Brownian motion model for trait evolution. And this model has been a workhorse in phylogenetics and the phylogenetic comparative methods since the early 70s. And it's very, very appealing because the Markov structure allows for very efficient pruning algorithms for computing its likelihood and performing inference. There are some weaknesses associated. This model doesn't take into account any sort of a Hello. Hello.
Hi.
Can you hear me? Hi there.
Yeah, I don't know what happened. Did you lag, or did I lag, or did everyone lag?
I think it might have been my connection.
Okay.
So I said I'm not sharing any screen there, I think.
Yeah, you aren't sharing the screen at the moment. Yes, I see now. It's just not full screen.
It's not full screen. Sorry. Is this a modeling trait evolution?
I see repeated measurements kernel is what I see.
Sorry, I think I'm sharing the wrong screen there. Repeated measurements kernel. That's where are we? I'm sorry about this.
No worries.
What's going on? It's not giving me the. Okay, I'm going to go to the repeated measurements kernel. I'll go full screen. I hope. Okay, so are we at modeling trait evolution?
Yes.
And it's not a full screen, I'm afraid, isn't it?
No, it's not, but it's okay for me.
It's almost full, so that.
Yeah.
Okay. I'll continue. Sorry about that.
No worries.
Well, I was saying that we had the Markov, we had a Brownian motion model for trait evolution that is very appealing due to its kind of efficient inference that we can perform using it, but it is some of the weakness to do with how robust outliers it is. And that it doesn't account for natural selection. So one extension or one approach to addressing one of these problems, that is the effect of natural selection, or what's referred to as stabilizing selection, is to use the Ornstein-Uhlenbeck model for trait evolution. So that is to say that we include a strength selection parameter alpha and an optimal trait value mu, and at each step there's some force encouraging the trait value from one generation to the next towards this optimal, and this results in a stationary Gauss-Markov process, which you can see if you look in the figure at the bottom here, comparing the Ornstein-Uhlenbeck process. So these are 100 samples from Ornstein-Uhlenbeck to 100 samples from a Brownian motion, and you can see that the Ornstein-Uhlenbeck is stationary through time, whereas the Brownian motion tends to, as time increases, the variance of the process increases. And this can be quite appealing when we are modeling evolution. It gives us an extra bit of flexibility because as alpha, the strength selection parameter, tends towards 0, the Ornstein-Uhlenbeck model does actually tend towards a Brownian motion. Okay. So another way of thinking about these models for evolution is as a phylogenetic Gauss-Markov process, and these models are actually due to Jones and Moriarty. They were a paper that was written in 2013, I think. And the idea here is to define a phylogenetic covariance function. The form of which is given, kt here, is the exponential of minus the patricitic distance dt over the phylogenetic length scale. So the patricitic distance simply defines the distance between any 2 points over the phylogeny. So in this case, the distance between point T on the phylogeny, Ti and Tj on our phylogeny here is simply given by lowercase ti plus lowercase ti plus 2 tij, where the lowercase t's denote the time from the root of the phylogeny to a particular point. And this is a really nice way of thinking about these models for evolution, because it opens up the kind of kernel methods for Gaussian processes that are fairly well established within machine learning. And this was actually the context which these models were proposed. They were actually proposed for modeling function value traits. So the idea of a function value trait is this is a trait which is observed, which is potentially continuous over some trait space. And this can be defined, a model for these function value traits or multivariate traits can be defined given a trait phylogeny covariance function. Again, the appeal of this is that it opens up the possibility of using techniques from machine learning. When these were proposed, they focused, Mr. Jones and Moriarty focused very much on the separable trait phylogeny covariance function. So that is to say that we can separate out the covariance function into covariance over the trait, so that a kernel for the covariance over the trait and a separate kernel for the covariance over the phylogeny. And while this is useful and it'll give us a way of thinking about function value traits and multivariate traits, it doesn't give us the flexibility that we'd really like to have when modeling evolution. For example, it doesn't really allow you to include independent observation noise for the traits, and perhaps we want to be able to include some sort of combination of kernels that are maybe built around a separable trait phylogeny covariance function, but are then in combination are not necessarily separable anymore. Okay, so this takes me on to my own work and what we look to contribute. So we look to make 4 kind of contributions here. The first was to be able to include discrete traits within this model for evolution. So to be able to model any collection of either categorical or ordinal traits alongside continuous and function value traits. We wanted to move beyond this separable trait phylogeny covariance function to consider a more flexible model for evolution. We also want to be able to include repeated measurements at X and taxa, because in a lot of cases when phylogenetic comparative analysis was done, the traits corresponding to each species would simply be averaged, and it'd be nice to be able to really include information as to how many measurements have been taken for each species, and include that within our model. And on top of all that, we want to be able to perform Bayesian inference in an efficient manner, to create a practical tool for big data applications. Okay, so I'm going to address each of these in turn. I'm just going to kind of introduce the ideas without necessarily going into the details. The first of these is to be able to incorporate discrete and continuous traits within a single model. And the way we did that was to take a data augmentation approach. So the approach here is simply given a matrix Y of n observations of D traits. These can be ordinal, categorical, continuous, or function valued. We assume that each of the observed traits correspond to some set of auxiliary traits X, which are defined over the real values, real numbers. So that is n auxiliary traits of length d prime, where d prime will be greater than or equal to d, depending on the structure of the manifest traits that we are considering. So the idea here is that as these auxiliary traits cross particular thresholds, this allows us to map them into discrete space. And so for ordinal traits, it's simply just as they cross the threshold. For categorical variables, where the categories are not necessarily ordered, you would have one auxiliary variable for each category, and the maximum of those auxiliary variables then denotes which category the trait falls into. The appeal of this is that it gives a kind of a probabilistic method of defining the discrete traits, the distribution over discrete traits, and this is just a probit regression, and it opens up means that we can then simply apply our models for continuous traits to the auxiliary traits. So that's the first thing we wanted to do. Next, wanted a method that moved past the separable trait phylogeny covariance functions, and to do that, formulate what I'm calling the generalized phylogenetic latent variable model. So this is a model for the auxiliary traits, and here we model auxiliary traits as a linear combination of loadings W and latent variables, a q-dimensional, where q will be much smaller than d, q-dimensional vector of latent variables, and then include some observation noise on that. The latent variables will be within the model the evolution of traits. These are kind of latent traits. We'll model the evolution of traits over the phylogeny, with the loadings W then projecting these latent traits into the manifest or into the auxiliary space, which then get projected into the manifest space of traits. And this is a really nice flexible way of moving beyond the separable trait phylogeny covariance function while preserving a fair amount of interpretability as to what is actually going on under the hood. So this is just a factor model, very similar to probabilistic PCA and these kinds of things. So in terms of the actual formula and variables, I'll get into that in a minute. But first, I just want to talk a little bit about how we model the repeated measurements, because that was the third thing we wanted to do. We wanted to include repeated measurements for extant taxa. So what I've illustrated here is just a toy phylogeny where we've got 2 internal nodes and 4 nodes for extant taxa. So these are our existing species here for v n+1 to v n+4. These are so in the concept of bats, these are just existing bats. And between those, between the extant species and the ancestral species at the internal nodes, we have some branch length. So we know that the evolutionary time between the different species and their ancestors. However, we have a situation where there's been some arbitrary number of measurements made for each species, and the approach we took to including that was actually to just think of it as a number of branches of length 0 attached to the nodes for the extant species, and then using that we can actually go ahead and define a kernel which links the phylogenetic covariance function to this phylogeny, incorporating repeated measurements for the extant traits. So this is the form of the kernel. It's a slightly ugly expression, but it accomplishes a couple of things. The first thing it accomplishes is the maximum of this kernel is 1. That occurs because we've got 3 parameters. We've got kappa, we've got tau, each of which is restricted between 0 and 1, and we've got the phylogenetic length scale L. So in this case, kappa can be thought of as the heritability of the trait. So you can see here that kappa is we've got the product of kappa and the kernel, the Ornstein-Uhlenbeck kernel. So kappa can be interpreted then simply as the proportion of variation over the phylogeny, which is due to the phylogenetic Gaussian process. Then the 1 minus kappa would be the proportion of variation within the trait for each species that are due to non-phylogenetic environmental effects. And then finally, tau will allow for the within taxon variation. By including tau, we can actually include these repeated measurements, which may vary slightly from one observation to the next. And this kernel provides us with a really, really flexible model that can fit to data even when the the data we observe is not, strictly speaking, doesn't necessarily follow an Ornstein-Uhlenbeck model for trait evolution. It can accommodate that through the inclusion of these extra parameters, kappa and tau, to model other effects for in the process. So we can now include repeated measurements within our model, and we can use that to model the evolution of our latent traits over the phylogeny. And to do that, we simply let the latent trait variable Z be given to be modeled as a phylogenetic Gaussian process so that is a Gaussian process over the phylogeny. By modeling this way, we then can introduce more latent variables corresponding to the internal nodes of our phylogeny. This means that we can define a matrix of latent variables Z, which has rows corresponding to each of the observed traits, but also each internal trait. So that is the internal traits corresponding to each existing species. The internal nodes of the phylogeny can for each extant species, but also then the ancestral species that are there as well. And the nice thing about this is that it allows us to exploit the Markov structure and come up with a fairly efficient method for inference. So I'm just going to talk a little bit about the inference. The approach that we took was to use to come up with a mean field variation inference scheme to optimize the evidence lower bound. So to do this, we had to define prior distributions for the loadings, for the observation noise, for those parameters that are involved in the mapping from the auxiliary to the manifest variables, and also for the phylogenetic hyperparameters. And it's so when we do this, if we choose a Gaussian prior for the loading, for each loading, with a automatic relevance determination prior for the variance of this of each loading, for the variance in the prior of each loading, this allows us to prune away superfluous dimensions of superfluous latent variables within the inference, which simplifies our model selection down the line. We place beta priors on kappa and tau, given that they are restricted to between 0 and 1. We choose a gamma to 1 for the length scale. This is important. This eases the kind of problems of identifiability in the inference. That's why we pick something that's quite informative. And the way this can be interpreted is saying that over short timescales, our Ornstein-Uhlenbeck is very close to, or behaves similarly to, a Brownian motion. Finally, then, just place gamma priors on the precision matrix for the observation noise, and the gamma prior on the automatic relevance determination parameters. And when we do this, we can actually get closed form approximate posteriors for the latent variables, the loadings, and the observation noise. We can get an expression, an unnormalized expression for the approximate posterior on each of the phylogenetic hyperparameters. And during the algorithm, we just optimize those at each step with respect to the elbow. But once converged, this expression will allow us to actually perform some sort of uncertainty quantification on those hyperparameters. Okay. So I'm just going to demonstrate or talk about the data applied to a synthetic data set, just to justify the use of this model. So here we simulated a data set. So we simulated a phylogeny which had 128 extant taxa, which included 3 observations for each of those taxa. We then assumed that the evolution occurred according to a phylogenetic latent variable model with 4 latent variables. The loadings for each of those 4 loadings are illustrated here in plot B. And then we assume that each of the loadings, or each of the latent variables corresponding to those loadings, were independent with the parameters, the phylogenetic parameters given in the table here on the left. And simulated our data, and that data can be seen there in figure C. So this data included an ordinal trait, a categorical trait, a continuous trait, and function value traits. And so we decided to perform inference on this model, given the phylogeny, with a random initialization of the for the variational inference. Just initialize the loadings at random, and this is the output. So in the top left-hand corner, you can see that this illustrates the posterior distribution for the reconstructed for the ancestral trait. So that is the trait at the root of the phylogeny, and so you can see that for the ordinal trait, our approximate posterior is nearly indistinguishable from the truth, and this holds for our continuous and function value trait as well. There's a small bit of difference in terms of the categorical data, but this the main thrust of this doesn't affect our interpretation of the posterior, and this is a really nice result. This was just a random initialization, and it shows that we can actually reconstruct the ancestral distribution to a fairly high degree of accuracy in a very efficient way. This model will fit the data in around about 20 minutes for this particular example. Okay, so I'm just going to take a minute there if there was any questions on any of that. No? Sorry. Okay, well, in that case, I'll continue and I'll talk a little bit about signal processing. So first thing is that bad echolocation calls are acoustic signals, and there's a lot of research being done in this area, particularly with respect to kind of speech analysis and things like that. And what I'm illustrating here is the spectrograms corresponding to a set of to 4 different bad echolocation calls, and the spectrogram gives us a time frequency representation of those echolocation calls, and this allows us to see the kind of time frequency structure, so that we can see the very distinct frequency components, which consist of frequency modulating components, but also constant frequency, and you can see also that these tend to be multi-harmonic calls. They also last for various different lengths of time, and so what we want is a feature representation of these echolocation calls that allows us to include the harmonic order, which of the harmonics is the dominant one, so which carries the most energy. As you can see here for Terminodus parnelli, it is actually the second harmonic seems to have the most energy, whereas for Anthrosus pallidus it's the first. We are interested in that. We want to know how long the calls last for, and then we also want the fundamental frequency curve, because this fundamental frequency curve will tell us the information we need to know about the shape of the frequency components and how these frequency components change through time. So in order to define these, use a harmonic model. So given here is a harmonic model for a real valued sinusoidal signal, defined over some interval 0 to t, and this is given by taking the harmonic order k, so the sum over each of the harmonics, by the amplitude envelope, which tells you the kind of the energy within, or is approximate to the energy within each component, and the instantaneous phase, so that's ak, and then the instantaneous phase phi k. And this is what defines the frequency components, so the rate of the sinusoidal oscillations. Here, phi k, the instantaneous phase, is defined by the integral from 0 to t of the instantaneous frequency fs. So this instantaneous frequency is the instantaneous fundamental frequency. This is the frequency curve that we are interested in and will characterize the frequency structure of the call. So what we really want to get access to is fs here, that function, k, the harmonic order, the amplitude envelopes a, would be great, and also the duration. Now, this model, as I presented it, is very problematic because it's completely non-identifiable in that there's an infinite number of combinations of amplitude envelope and instantaneous phase that will actually map to Y. So inference is a very, very difficult problem. So in order to approximate this, what we did was considered windows of the signal that we're interested in. So consider the sinusoidal signal Y that we've observed, discrete observations of the signal, and then we let xn be the nth window, where each of the x's define all the x's together define a set of overlapping windows spanning the signal Y, where x is given by a set of sinusoidal bases where the basis coefficients are given by beta 1 and beta 2, and the harmonic order is given for that window is given by kn. The fundamental frequency for that window is given by fn, and there's some noise in the observation. And this effectively assumes that each window, that the signal is stationary within each window. And making this assumption, we can then estimate a fundamental frequency for each of the windows we're concerned with. So in order to do this, what we did was we set a Markov prior for theta, where theta is the combination of basis coefficients along with the harmonic order kn, fundamental frequency fn, and the observation noise sigma n. And we just said that the prior for these components would depend on the values of the previous window. This allows to enforce some sort of smoothness on the fundamental frequency. Okay, so again, without getting into the weeds on this, we can define a model for each window, and with using a judicious use of priors, which involves a Zellner G prior for the basis coefficients, we can actually marginalize out the observation noise and those basis coefficients. It means we try to infer the fundamental frequency and harmonic order directly. That has to be done by a grid search optimization. That's just the approach we have to use. So it's not an especially efficient approach, but it does allow us the level of precision that's needed for an application like this in most cases. So just to show you some of the results and how they work out, fitting this model to a set of echolocation calls, we can see for Meagher Voland that it picks out the fundamental frequency component really, really well. Then moving on to Balantiplerix plicata, again, does a great job. Petronos Parnelli, fantastic job. Tadarita brasiliensis, unfortunately, it doesn't do so well. Now, the problem here is that the signal to noise ratio is quite low. This makes it quite a difficult problem. And in our application here, we really want a precision about the fundamental frequencies, because if we get those wrong, it will affect our inferences right up the phylogeny. So in this application, I actually did a post-hoc correction, which involved cutting out windows that had a very low signal to noise ratio in it. So in this case, we would remove some of the windows at the start of the Tadarita brasiliensis call, which seems reasonable enough if there's not enough signal to pick up on, and then effectively kind of lining up the fundamental frequencies as we move through the other windows. It would be nice to incorporate all this within a single model, and that would be something for future work, but doing that did allow me to actually pick out a fairly satisfactory representation of the fundamental frequency. So given this fundamental frequency, we can then actually get amplitude envelopes for each of the components, harmonic order. We can figure out which is the dominant harmonic, so which one contains the most energy, and the duration of the call. So they're the features that we're interested in. So given all that, I can actually move on to the reconstruction of the BAT echolocation calls. So just a quick recap, we've developed a flexible model for evolution of any collection of discrete or continuous traits over phylogenetic. It's flexible in that it allows for both non-phylogenetic and intrataxon sources of variation. We've got an efficient inference scheme, which is variational inference. And we've then identified the characteristics of the BAT echolocation call that we're interested in, developed a harmonic model, which actually defines these traits mathematically. And the inference scheme we did was a maximum a posteriori inference scheme, and along with a post hoc correction. So the data that we actually fit this to was a data set of echolocation calls gathered from across northern and central Mexico. This was publicly available. Each of these calls sampled at 5,000 kilohertz, which is appropriate for BAT echolocation calls, given that they range from like 9 to 212 kilohertz for their dominant components. The data set included 1,800 calls from nearly 500 individuals across 22 different species and 5 families. So it provides a relatively small data set in terms of the number of species covered, but this is quite a large data set in terms of the data being included in our model for evolution. So there was up to 100 calls per species, and we wanted to include all of those that we possibly could. Okay, so the specification model. So the features that we used are the fundamental frequency curves. So that's a function value trait. These have been time registered, just a technique from functional data analysis. We wanted the duration of the call. This is a continuous trait. We wanted the harmonic order, which was treated as an ordinal trait in that it moved in order from between 1 and 7, I think we allowed for, is the maximum harmonic order, and a dominant harmonic. So we treated this as categorical, just whichever one would be the dominant harmonic. For the variational inference, in this case, we did an exploratory sort of PCA of the data, and then initialized the algorithm, the inference scheme variation inference, with 8 latent variables. This is an overspecification. We then just decided we'd let the ARD priors prune away any superfluous latent variables. And these, the initial loading was obtained by a varimax rotation of the first 8 principal components, and we put that into the model. So the results, the first set of results I'm going to show you are just the phylogenetic hyperparameters. So just to remind you that we've got the phylogenetic length scale L. So this is the Ornstein-Uhlenbeck process parameter that tells you how persistent the correlations are over the tree. So it's a kind of a phylogenetic high length scale corresponds to a high phylogenetic signal. I've got the heritability kappa, which tells you the proportion of variation of the traits that are due to phylogenetic effects. That's a number between 0 and 1. Got the intrataxon variation, again, another number between 0 and 1. And this tells us the level of variation that's due to, that occurs within each taxon. So looking at tau, we can see for each of the latent variables, this is close to 0, very close to 0. This tells us that in the latent space, at least, there's not a huge amount of variation within taxa. This is good. It tells us that we can rely on to some extent on the correlations have been found by, or the relationships that are implied by kappa. And for kappa, we find that, the heritability of each of these latent traits is very high, close to 1. So that says that most of the variation of latent variables is due to phylogenetic effects. And then in this case, then the length scale is also quite high, all above 2. So it says that there's a stronger, this is just kind of a stronger degree of correlation, or a stronger relationship between traits than you would expect for a Brownian motion model for evolution. Now, I would say that interpreting these, I wouldn't place too much weight on these interpretations. This is just kind of something to check, just to see if there are phylogenetic signals within the data. But this says that, the reason I say you need to be careful interpreting this is because there is an interaction between the latent variables and the loadings. So very, very small Any variables could simply correspond to quite large loadings, but it would be, it does say that we can have some sort of, there will be some phylogenetic signal we can pick up on looking at these. Okay, so here I've plotted the results as best I can. So I'm going to have a look at the Pteronotus family first. So these are Melicidae bats. We can see their position on the phylogeny down here. So this is Pteronotus parnelli. And these three plots here, the posterior harmonic trace, posterior call duration, posterior fundamental frequency, these plot the characteristics of echolocation that we've been interested in modeling. So you can see that the duration of this call lasts between about 10 and 20 milliseconds, so it's a relatively long echolocation call. You can see the dominant harmonic here is typically the second. It's usually the second is the dominant harmonic for this species of bat. And then you can see the harmonic order is usually either 2 or 3. Plus the fundamental frequency shows that we've got a long constant frequency component followed by a kind of a bit of a sweep at the end. But the easiest to interpret bit, I think, is this bit here. This is the spectrogram. So this is a reconstructed call sampled from the posterior distribution for this species. So you can see here, yeah, we've got the 2 frequency components. The second one seems to be dominant with a constant frequency and a sweep at the end. So just to compare that with some of its closest relatives, so Pteronotus davii. So we can see that we can see that this is a constant frequency with a kind of a frequency modulating component bit in the middle, followed by another constant frequency. And you can see, and the duration is actually less than 10 seconds typically, 10 milliseconds typically. And again, the sample here illustrates exactly what this call tends to look like. And finally, we look at Pteronotus davii, which is this is what I'm on. Personatus. So yeah, we can see this one tends to have a kind of a bit more of a broadband sweep going on. It tends to start at close to 50 kilohertz and sweep down towards 30. And again, it tends to be under 10 milliseconds. So if we follow that up along the tree, we can see the most recent common ancestor for those 3 species is at node number 30. And yeah, so this is a sample call. So we can see that the call is most likely some sort of a sweep, broadband sweep, although close to a constant frequency, and tends to be shorter, so it tends to be under 10 milliseconds, which is kind of what we'd expect. The key one of interest is the most recent common ancestor of all these bats. That's at node 23. And that has not, I'm a bit surprised at the sampled result there. I usually see something much cleaner. But this result indicates that we see a relatively short call, so between about 3 and 7 or 8 milliseconds long. That it is a broadband sweep, that it goes from about 50 down to about 30 kilohertz. It tends to have about 3 the harmonic order of 3, and the dominant frequency is most likely the first, but could actually, a dominant component could also be the second. And I think my audio wasn't working correctly before the talk, but I think Massey should be able to play back that sound to you if you wanted to actually listen to it at a slowed down sampling rate. So if Massey wanted to go ahead and do that, that would be great. Yeah. So if you could maybe set the playback sampling rate to 5,000. Yes. And there you go. So that you can hear there, hopefully, is the sound of a broadband sweep. The ancestral echo bat, which lived approximately 52 to 66 million years ago, most likely had a call that sounded like that, only at a much faster rate. So yes, So there you go. That concludes my presentation, and I'd be happy to take any questions at this stage.